Hello, welcome to all of you. Now we discuss about Poincare-Bendixson theorem. First, we discuss about semi-orbit, limit set, and etc. etc. Half path of semi-orbit means let C be a path of the system, nonlinear system, first order differential nonlinear, dx dt equal to pxy and dy dt equal to qxy. And let x equal to ft, y equal to gt be a solution of the system 1, defining the curve of trajectory c. Then the set of all points of the trajectory c for time t greater than equal to t0, where t0 is some value of t is said to be half path or semi-orbit of the system 1. That is, the set of all points at gt, these coordinates of the points, for t0 less than equal to t less than plus infinity, which is denoted by c plus, because here t0 is the initial time and this is the from t0 to plus infinity. So we say this c plus, and we for the limit we say this path is segment of the path is c minus when minus infinity less than t less than t0. For this time interval, we say this path is c plus. So actually, trajectory c, this trajectory c is the union of these c plus and c minus. Consider this page portrait. Some example: dx equals to say y plus x bracket 1 minus x square minus y square divided equal to minus x plus y into 1 minus x square minus y square. In this page portrait, if we draw curve, this path, suppose this point is t0. So from t0 to plus infinity, this path is c, c plus, and minus infinity to less than t0. So this path is t minus. So suppose this is t. This point is t0. So this portion t0 to plus infinity, this portion of this path trajectory is c plus, and this minus infinity to t0 less than t0, this path is c minus. Suppose this point is t0. So suppose let this point is t0. So then for this path, this point c0, this point t0, from this point time t0, initial time t0. So t0 to plus infinity, this path is c plus, and on this trajectory, this minus infinity to t0 less than t0, this path is c minus, and whole trajectory is say c. Next, limit set of C plus. Let C plus be a half path of the system 1, this nonlinear first order differential equations, defined by this x equal to ft, y equal to gt for t greater than t0. And let x1, y1 be a point in the xy plane if there exists a sequence of real numbers Tn n equal to 1, 2, dot, 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 to infinity, such that Tn tends to plus infinity, and this sequence of points ftn, gtn tends to x1, y1 as n tends to infinity, then this point x1, y1 is said to be a limit point of C plus. The set of all limit points of C plus will be called the limit set of C plus and will be denoted by LC plus. Consider this example, dx equal to this, and the solution of this equation is this, taking a constant, say k equals to 1 here, this constant k equal to here, and the set of all points of the trajectory C for t greater than 0 is a half path C plus. That is, the C plus is the set of all points in the coordinates cos t by root over 1 plus e to the power minus 2t, comma minus sin t by root over 1 plus e to the power minus 2t, 0 less than equal to t less than infinity. Here t0 is the 0. So all points, collection of all points is the set C plus, is the half path C plus of the trajectory C. And consider the sequence, this this t equals to 0, t equals to 2 pi, t 4 pi, 2n pi, and dot dot to infinity, tending to plus infinity, as n tends to infinity. The corresponding sequence of points on C plus is is this sequence of points n equal to 0 to 1 to infinity, and this sequence approaches to the point 1 0 as n tends to plus infinity. Thus 1 0 is a limit point of the half path C plus. The set of all limit points of C plus is the set of all points such that x square plus y square equal to 1. So x square plus y square equal to 1 is the limit set of C plus. Consider this phase plane, this, if we draw this path, this. So this path, this point is t equal to t0. So from this t equal to 0, so t0, say, this path is going to this point. So when tending to this point is 1 0 point. So for this path, for this C plus, for this portion, this tending to the point this. Say another path, this also tending to the point 1 0. This is the xy plane, this x-axis and this y-axis. This is the origin O. So this point is 1 0. So for this path is this tending to 1 0 point. So this is the 1 0 point, is the limit point of this. So for the other trajectories of this system dx equal to this, and we get the collection of all limit points, limit set of this system. We draw all trajectories. So we get a beautiful design. These are all these points on this circle, unit circle with radius 1 at origin, center at origin. So this is the limit set of this trajectory. This point is 1 0, and this point is 0 1. This point is minus 1 0. This point is 0 0 minus 1. So this circle, unit circle, x square plus y square equal to 1 is the limit set of this system. So x square plus y square is the limit set of C plus. C plus. Next, we discuss about Poincare-Bendixson theorem. There are two forms. First, strong form, and second is weak form. First, strong form. First hypothesis. Suppose the nonlinear first order autonomous system dx equal to pxy and dy equal to qxy, where p and q have continuous first order partial derivative in the domain D of the xy plane, and D1 be a bounded subdomain of D. So this D1 is a bounded subdomain of the domain D. And let capital R denotes D1 plus its boundary of this. D1 is the subdomain of D and this. So here PQ are continuous first order partial derivatives in the domain D etc. Let C class defined by x equal to ft and y equal to gt, t greater than t0, greater than equal to t0, be a half path of the system 1 contained entirely in R. Suppose the limit set LC plus of C plus contains no critical point of 1. Limit sets LC plus of C plus contains no critical points of 1 in this region. This. So, conclusion, either the half path C plus is itself a closed path. In this case, C plus and LC plus are identical, or LC plus, limit set LC plus, is a closed path that C plus approaches spirally from either inside or the outside. In this case, LC plus is a limit cycle. Thus, in either case, there exists a closed path of 1 in R, this region R, closed path in R. So from this theorem, we discussed about this. Consider the system is defined by in this region D, and this is the so this region is R. So this D1, this D1 is this region. This region is D1, and suppose this is critical point origin of the system, and this annular region is D1, and R is the this circle C1, and so this circle is called C2. So R is the region. This D1 is the bounded subdomain D1. Whole domain is D. Whole domain is D. Within which in the xy plane, the whole domain is D. Within which this P and Q for this system, x dot equal to P, and x dot means dx dt, and y dot equals to Q. This system. So this is the x-axis, and this is the y-axis. This is the y-axis, and on this xy plane, this domain is D, on which this P and Q have continuous first total derivatives. And this D1 is the bounded subdomain of the region D, and R denotes the this domain subdomain D1 with its boundary C1 union C2. So R is the bounded subdomain. This is the shaded region, and this boundary C1 inner circle and outer circle. This. So R is the region bounded subdomain D1 and this. And this let C plus be defined by the some trajectory. That's this point. Say this point trajectory is this point. Say suppose this point, this trajectory is this trajectory of this system. This now this point is called t equal to t0. At this point t equal to 0. So this portion after t0 less than equals to t less than infinity, for this time this c plus this c is the whole trajectory is this, for this trajectory is this. So this trajectory this trajectory of this trajectory is this. So this trajectory is this green color is C plus. This C plus for this initial time t0, t less than equal to t less than infinity. And this portion less than this portion is C minus. This minus infinity less than t less than t0. So from this t0, this point t0 to this portion. Now C plus denoted by this, and suppose the limit set LC plus of C plus contains no critical point of this limit set LC plus. So for this C plus, for this trajectory C plus, suppose this is the limit point. This limit point is. So for another trajectory, for this, another trajectory, this. So enter in this region R. So we get another trajectory is this. For this another trajectory is this. C plus. So set is this T0, so C plus. So this is the limit point of this after T tends to this point this. So in such a way this conclusion is that either the half path C plus is itself a closed path, or LC plus is a closed path which C plus approaches spirally from either inside or outside. So collection of the this limit point of this, so we get this limit point of this trajectories. We get this red set point set this. This is the closed path of this. The collection of all these limit points of this. This is the LC plus. This is LC plus. So this LC plus is a closed path for this system where x dot equal to p, y dot equal to q. Either from outside this entering this region outside, or from inside, or from inside. So this inside this up to this infinity. So from this inside from this and from outside this. So within this region R, we get a closed path LC plus. This closed path exists. If in this region R, there exists no critical point of the system. We are consider only 0, 0 is the critical point, say, is the only critical point of this. So within this region R, there is no critical point. So if there is no critical point of the system in this region R, this annular region R, then the path, then the half path C plus, this is path is C plus and this path is C minus. So this is the whole trajectory is this for any particular constant value. So this C plus is limit cycle. This is red path is called a closed path. This closed path exists for the system this, and this is called second. This is limit cycle. Actually, by this theorem, we get a closed path, and by H-plane plotter for the example, this limit cycle is this is the limit cycle is, and consider the another definition for this. Conclusion: either the half path C plus is itself a closed path, or LC plus is a closed path which C plus approaches spirally from either the inside or outside this path. Poincare-Bendixson theorem, we form hypothesis exactly same as the strong form. This is the hypothesis 1 and 2. This hypothesis and conclusion for the strong weak form conclusion is: if R contains, R means the region, this bounded region with its boundary, a half path of 1, say suppose C plus, then R also contains a closed path of 1. If R contains a half path of the system 1, contains no critical point, R contains no critical point. R is the annular region of this. Contain no critical point of worm. And conclusion, if R contains a half path of C1, then R also contains a closed path of worm. Now, note that it is the difficulty in applying the theorem we form usually comes in being able to show that the half path C plus is entirely contained in R. If we can show that vector pxy and qxy, this vector determined by the system 1, points means directed into the region R, interior of R, at every point of the boundary of R, then the path C entirely R at t equal to t0 will remain R for t greater than t0, and hence provided the needed half path C plus. So this vector PQ, this vector point determined by 1 points into R at every point of this boundary R. Then the path C entering R at t equal to t0, at the point t equal to 0, path C entering the region R, path C means trajectory C of the system, will remain in this region R for time t greater than t0, t tends to up to infinity, and hence provided the needed half path C plus. So then we get then the all half path exist in this domain C domain R. Consider this example dx equal to y plus x minus x bracket x square plus y square minus x plus y minus y x square plus y square. Using Poincare-Bendixson theorem, uh, this system has a closed orbit. First we find critical point, say x star y star be critical point of the system, then dx dt at the point x star y star equal to 0, dy dt at the point x star y star equals to 0. Obviously, 0, 0, the origin is the critical point of this system 1. Now we want to transform the system 1 into polar coordinates, and for that we use x equal to r cos theta, y equal to r sin theta. Here r is positive quantity greater than 0. And so r square equal to x square plus y square, tan theta equal to y by x. Now x dx dt plus y dy dt, and this equals to dx dt, put the value of dx dt and dy dt from the 1, and after simplification we get this result. And so these are dr dt, because r square equal to x square plus y square. So twice r dr dt equal to twice x dx dt plus twice y dy dt. Cancel 2 from both sides. So we get r dr dt equal to x dx dt plus y dy dt. So x dx dt plus y dy dt equal to r dr dt. And this x square plus equal to r square, and this 1 minus r square. So cancel r is positive quantity. So here dr dt equal to r 1 minus r square. And also, we get y dx dt minus x dy dt equal to x square plus y square. Similarly, if we put dx dt equal and dy dt value from the system 1, and after simplification, we get this result. Now, y dx dt minus x dx dt, put the value of y, r sin theta, and dx dt equal to minus r sin theta d theta dt, and x equals to minus r cos theta, dy dt equal to r cos theta d theta dt. So, after simplification, we get minus r square d theta dt. So minus r square d theta equal to r square. Cancel r square from both sides. We get d theta equal to minus 1. And d theta is equal to minus 1. That means theta is in clockwise direction. Anti-clockwise direction is plus. So clockwise is minus. Clockwise direction in this direction. So the given system 1 becomes into polar form. This dr dt equal to r1 minus r square, d theta equal to minus 1. Now we consider the annular region R. This is the annular region R. r equal to half. So this dotted circle is r equal to half, and this r equal to 3 by 2, this dotted circle. So within this region, half is less than equal to r, less than equal to 3 by 2. So this is the annular region, bounded annular region is called R, capital R. On the circle C1, that is the dotted circle, inner dotted circle C1, R equal to half, that is x square plus y square equal to half square. dr dt equal to R1 minus R square. So on this circle, half into 1 minus 1 by 4, so this is greater than 0. So greater than 0 means, so R is increasing. dr dt is get positive, so R is increasing. So the vector px pq points directed into R at every point of this inner circle. So is outer direction on this inner circle, because this is increasing direction. So R is increasing direction means this is the away from origin. So this is the this outer direction on this circle R equal to half. And on the circle C2, where R equal to 3 by 2, dr dt equals to, say suppose 3 by 2, put there r into 1 minus r square, so we get negative sign. So r is decreasing. So for decreasing, this is the towards origin. So on this circle C2, r equal to 3 by 2, this direction is inward direction. So by this inward direction, so trajectory enters in this region, angular region R. And where this trajectory C enters in the annular regions at this time t equal to t0. So from t0 to after that portion to infinity for this portion is c plus, and before t0 this portion of this trajectory is c minus, and after entering this portion, this trajectory c plus lies within this annular region, because here this uh, critical point, does not lie in this annular region. Hence, R is the annular region between these two circles C1, C2 and their boundaries. Clearly, this annular region R does not contains no this critical point 0, 0. So, by Poincare-Bendixson theorem, we form this path C entered in this annular region R at the point t equal to t0, this point where this trajectory enters in this annular region t equal to t0, will remain in R for t greater than t0, greater than equal to t0. And this provides us with the needed of half path C plus contained in R. So C plus trajectory, portion of this trajectory C plus, always in this R after this. Now, the Poincare-Bendixson theorem we form is this. Already we discussed this. D1 is trajectory. Is R is also contains a closed path of this system. So, by this theorem, we can say we must have a closed path of the system in this angular region. Poincare theorem states that we must have a closed path of the system within this angular region. Obviously, you can solve easily from this. We can get this x square plus y square. Actually, this is the closed path. Actually, this is the stable limit cycle. Already discussed in the stable limit cycle chapter. This, so x square plus y square is the stable limit cycle of the system. So here, so entering this region, so this is the stable limit cycle of this. And if you draw a trajectory from this inner point, this origin, so this also tends to the stable limit cycle this. So this is, we get a beautiful picture of this. So this is the critical point origin, and this from this inner side, these trajectories also go to this limit cycle of this x square plus y square equal to 1. Next example, using Poincare-Bendixson theorem, show that the following system dx/dt equal to this and dy equal to this has at least one periodic orbit in the annular region 1 by root 2 less than equal to r less than equal to 1. First we find the critical point 0, 0 of this system and convert this system into polar form. So we get dr dt equal to r minus r cube bracket 1 plus sine square theta d3 equal to 1. So here positive sign. So this is rotation is clockwise direction, sorry, anti-clockwise direction. R is positive quantity. Now dr dt equal to this. So r minus 2r cube plus r cube sine cos cube cos square theta. So obviously r is positive. So r cube cos square theta is always positive for any value of r because r is positive here. So dr is positive when r minus 2r cube is positive. That is when r square is less than half, that is r is less than 1 by root 2. And dr equals to this. Obviously, this is negative if r minus r cube is negative because this minus r cube sine square theta is always negative. So r minus r cube is if negative, then dr dt is negative. So this gives r is greater than 1. So for r is greater than 1, so this is the annular region. This outer circle is r equal to 1. This inner circle, rotor circle is r equal to 1 by root 2. So outer circle r is negative. So negative means dr dt negative means r is inward direction, is in the inward direction towards origin inward direction, and dr dt is positive for this r less than equal to 1 by root 2. So less than equal to root 2 means this positive means r is increasing direction. So this vectors is outer direction, that is away from origin. So enter in this region. Merely the annular region R 1 by root 2 less than equal to R less than 1 does not contain any critical point. Obviously, 0, 0 is the critical point and outside of this critical annular region R. Also, as dr positive for R less than 1 by root 2 and dr positive less than negative when R greater than 1, all trajectories of the given system will remain in R for all time. If trajectory from enters from outside, then this within this trajectory, and from inside this from 0 this tends to enters in this trajectory. This trajectory enters in this region, annular region, all times in this region. Hence, by Poincare-Bendixson theorem, there exists at least one periodic orbit of the system of this annular region. So, if we draw this graph by phase plane plotter, system x minus y dx dt equals to x minus y minus x into star bracket x square plus 2 into star y square bracket close. And second equation is this dy dt equal to x plus y minus y into bracket x square plus 2 star y into y. X minus y minus x bracket x square plus 2y square, x plus y minus y x square plus 2y square. So, and d theta dt is positive. So here this is anti-clockwise direction. So we draw trajectories of the system, we get this picture is this, and from inside, so this is the limit cycle, and from inside we see that this, and from the inside all trajectories goes to this point. So we get a limit cycle. Obviously, this limit cycle is the stable limit cycle, and direction is anti-clockwise direction because d equal to 1 positive. So this from this we get the limit cycle is this closed path, actually closed path in this angular region. So by this Poincare-Bendixson theorem, we get a closed path in some closed region. If in this closed region R, if in this closed region R, there is no critical point of the system. Thank you.